Hi, in this video I'll discuss about what is model overfitting. You might have heard about what is a model overfit, and we'll discuss what is model overfitting, or when we say that a model is overfit, how do we detect such a problem in model, and how do we overcome this problem. First, we need to understand why do we build model. Why are we, interested in building a statistical or a machine learning model? There are two purposes, main purposes. One is the prediction. We want to predict a particular variable in future, and we also want to find relationships. So that is covered in the inference part. So model could be built for only prediction, only inference, and could be built for both. Okay. So to understand, just to take an example, prediction problem could be predict sales of a particular product based on the different attributes of the product, advertisement, price, and so on. And then inference could be knowing what factors affect sales of the product and by how much. Okay, so this is where we're trying to understand the relationship between two variables, sales and the factor related to sales, like price of the product, the advertisement money spent on the product marketing, and so much, and by how much does it affect, or does one variable affect the other, or the dependent variable, which is sales, right? So these are two main reasons why we build models. And what is the intention? The intention is that we try to find a pattern in the historical data, and we try to generalize the pattern and apply that same pattern in future. We expect that the historical pattern will repeat in future. So that is the idea behind building a statistical model or finding out a statistical relationship. So the point that we should keep in mind is that building model is about generalizing relationship between your variables. Or if you're familiar with modeling, you know that you have a dependent variable and you have an independent variable. So we are trying to generalize the relationship between your dependent and independent variable. All right. So how do we come across such a problem? How do we come across the problem of overfitting? Now, the relationship that we are trying to generalize could be linear in nature or could be nonlinear in nature. The linear relationship will look like this. So here is a variable x and there is a variable y. Y is the dependent variable. So we are trying to predict y based on x. Now, if the relationship is the relationship can be generalized in a pretty linear way or in a straight line manner, then we call that as a linear relationship. And it is very easy to predict the value of y from the value of x if such a relationship exists. But in most scenarios, you won't find such a relationship. In real life scenario, you won't find a relationship that is completely linear. If that is the case, then there is no need of statistical modeling. You can simply find a deterministic relationship between y and x, and you can use that in future. Most real scenario are very random in nature, somewhat random in nature, and there are biases. Okay, there is non-linear relationship, and there is some sort of there are some observations which are considered to be sort of outlier, which come into the picture, or which may not be completely linear, as we can see in the first graph. The second graph is about a nonlinear relationship. So here is what it is. Okay, so this is a relationship which is not completely linear, as you can see. Now, to build some sort of a nonlinear relationship, and you will come across cases where most data or most relationship between your dependent and independent variables are nonlinear in nature. Okay, some would be less nonlinear, some would be more nonlinear. So the degree of nonlinearity will vary from one data set or one sample to the other, or one sort of set of variables to the other set of variables, but there will in most cases a nonlinear relationship between such variables. Okay, so in such a scenario you could completely find uh, a sort of a curve that fits into the data points, or just find out if at all there is a linear relationship that can be taken as somewhat somewhat um, generalizing the relationship between x and y, or there could be a relationship which is both linear and nonlinear, and you can use both. Now take for example, we are taking the YOLO curve here. Okay, so in this case the YOLO curve actually passes through all the data points, so that's a complete fit or the best fit curve that we are using here. Okay, and the second one is a line. Okay, now if you ask me which one is better fitting your data, I would any day say the YOLO line is fitting your data the most, because it is passing through all the data points and it is able to generalize the relationship in a better way than the line. Well, this is a situation known as overfitting. So here we have overfit the model, because the relationship that you are finding in the historical data may not repeat in the future data. So it is fitting the historical data in a pretty good manner, but not necessarily the same relationship will exist in future data. And we are only concerned about future data because the historical data is already with us. We already know the relationship. We already have the observations for the dependent variable. And all we need is finding such a relationship for future data, right? Or data that we haven't seen yet. We haven't seen it. And for that, we need to find more general relationship rather than a specific relationship. Here, the relationship is very specific. The YOLO line only captures the specific relationship between your y and x, whereas the straight line more sort of it generalizes. Okay. Now, it can be made better though. It may not be completely a straight line, or could be something like this. Now, which is a curve, but it's not completely passing through all the data points, right? It is generalizing in a better way. Now, whether a straight line will do a better job or a curve will do a better job, we'll see that. Okay, that depends on many reasons. In most inferential problems, you will go ahead with a straight line, whereas in prediction problem, you will go ahead with a curve. Okay, but ensure that your curve should not pass through all the data points and should not completely should not be an overfit, rather say. So this is a technical term that we use for fitting a model in such a way that it doesn't work well in the future data or new data or a data that is yet to be seen. Now this can well be felt in a classification problem. Now in the last slide we talked about a regression problem. So in a classification problem, now here is the case 1. In case A, and here is case B. In case A, where you can see this particular curve, classification curve, is able to classify the two sets of data points. Okay, and we have marked it in different colors. Now this might be doing well in a historical data, but in a new set of data, if such a model is applied, it may not perform very well. Okay, so to be very sure about the fact that the model will do well in future data, we should be able to generalize it. So how do we do that? We'll rather fit a line which would may not be classify all the data points completely. As you can see, some of the uh, some of the data points are like, this data point should be in the right hand side, this is also should be in the right hand side, but it's there in the left hand side. It's fine, few observation here and there, it's okay. That is considered to be a better model because it is able to generalize the relationship and something that can be used well even in new data or data that has not been observed yet. The same problem can also be felt in time series forecasting. So we can also see such a problem in time series forecasting. So overfitting problem is something that you can find in regression problem, in classification problem, and also in time series forecasting problems. You can also find such a problem in unsupervised learning, like clustering. You can also find such problems in clustering as well. Now, two main problems will arise if you were to use an overfit model for your data or for the problem that you are trying to solve. Okay. In prediction problem, you will face the bad prediction, or the prediction will be very inefficient. Okay. So the model will perform very badly with new data or in the future data. In the inferential problem, you will find a wrong relationship, or rather inefficient relationship between two variables. So if you are building a model y equal to beta naught plus beta 1 x, and it says that x and y are having a non-linear relationship, whereas they are having a linear relationship, having an overfit model can give you a very wrong relationship. Okay. Sometimes the sign of the the coefficient or the estimate could also be different if you are overfitting the model. So ensure that you detect such a problem in your model and overcome it, or just avoid it while building a model and finalizing it for use. So how does it happen? Why do you face such a problem while building statistical models? Well, it could happen for a variety of reasons. One of the reasons is having a small sample size. Many times you go ahead with a very small sample size to avoid computational, because many times if you have larger sample size, you will have the problem of high computational time. So you go ahead with smaller sample size, and that could be an issue. If you have a small number of data points and you are using large number of independent variables, so small sample and large number of features or independent variables, in that case you will have this problem. You will have the problem of overfitting. Okay. Other regions could be having or using nonlinear models. Some of the models which come under the nonlinear model category, especially the tree-based models, polynomial models, and these models, when used not very well, this could lead to model overfitting, which could do well in the sample data or in the training data that you are using, but may not do well in the future. Now we need to understand from an inferential statistic point of view why taking a correct sample could avoid overfitting. So the fundamental of inferential statistics says that we normally go in for a sample rather than taking population data for building a model, right? So this is our population, and we are taking a sample of it. We are taking just a sample of it to build a model, right? And based on what we infer from the sample, we extend that, or we extrapolate that for the population. Okay. Now, if you have taken a smaller sample or very small sample and with a large number of variables, you would come across cases where you will infer wrong informations or wrong theory, or you will validate some sort of a wrong relationship between your variables for the entire population. So ensure that you take a reasonably good sample that represents population. So the point that one should keep in mind that your sample should represent your population. Secondly, if you are using a large number of features or independent variable, make sure that you're having a very large sample. Okay, and it could be it could be very close to the population, or it could be the population itself, but ensure that you have a large number of observation, or you should have a good degree of freedom for it to be avoid overfitting. Now, how do we detect overfitting? Okay, we can detect overfitting by what is known as cross validations, by doing cross validations. Now we can do cross validation uh, in two ways. There are other ways also, but there are two ways of doing cross validations. One is known as the out sample validation. The other one is known as out times cross validation. So when we take a sample or a population data for building a model, we divide the model we divide the sample data into two categories. Okay, so we take 60 to 70%, the percentage could change though, 60-70% of the data for building our model, and we call that as a training sample, and we keep 40-50%, 30 to 50% of the data to test our model. Okay, we call that sample as validation sample or holdout sample. So we build model on the training sample, and we cross validate that, or we ensure that the model is working fine in the validation data. We ensure that the validation data or validation sample is not part of the model building process. So we do not use this data, this particular data, in training sample or while building model. So it's completely new to the model. Okay, so when you use that, we use a model in your validation sample and see that the model is performing very well there. So we are very sure that the model is not overfit, or we have been able to avoid overfitting. And if so, the model statistics should be consistent across training sample and validation holdout sample, to be sure that the model fitting is good, or the model is not overfit. We can also do what is known as out time validation. Okay, so what we do in out time validation is that we build a model on a particular time, a particular it could be time point, it could be a year or a month. So if it is a yearly, if it is a year, say for instance we build a model on 2010 data, and we ensure that the model is doing fine even on 2009 data, 2008 data, and so on. So we are building model on one time point, and we are testing it in different other time points. Okay. And ensure that 2009 is not part of your model data. The model estimation has happened only on 2010 data, but we are testing it on 2009, 2008, 7, and so on. And we should ensure that the model statistics are consistent, or the model is performing well enough in other. If there is a huge difference in the model statistics and the model performance statistics, whether it could be R square, whether it could be root mean square statistics, whether it could be C statistics, across this in sample out sample data, then you should go back and rebuild your model, and we'll talk about it, how we overcome such a problem, and how do we ensure that the problem doesn't arise at the first place. So you tabulate it actually. Okay, so you have statistics like R squared and regression. You have the parsimonious statistics like archaic information criteria, BIC, and you have the root mean square statistics, and then you you tabulate your values for R square for in sample and for out sample. Let's say for instance the R square value is 0.6 in sample and 0.62 in out sample. They're pretty same, right? So we're seeing that the model is pretty performing very well even on out sample data. But if it were like 0.5, so that is a huge difference. Now we should go back to our model building, and we should rebuild the model in that case, because in that case it's not a good fit. The model is seems to be an overfit. Similarly, we can also see for other statistics and should check whether the statistics performance statistics are consistent across the samples, in sample and out samples. So how do we avoid model overfitting? Okay, what should we do to ensure that the model is not overfit? So we should ensure that we have a large sample. So if we have large number of features or independent variable, we should take a large sample. We should only take best features, or we should only take the best set of independent variables which are helping us to predict the dependent variable. So we should have a proper feature selection in place while building model, and there are varieties of ways you can do. You can use stepwise regression, you can use forward, backward regression. Okay, so these are some of the feature selection. You can you can see the individual R square by doing a simple linear regression and take the one which is able to predict your dependent variable well. So you can use R square correlation values in order to select the best feature. You can combine feature also. You can also use PCA or factors analysis in order to combine features which could reduce the number of features or number of independent variables to a large extent. When you're using a nonlinear model, use it very carefully. So when you're using a nonlinear model, ensure that you're doing the cross validation very well. Sometimes you may need to do what is known as cross validation with multiple samplings. Like you could have a resamples, or sometimes we also call as bootstrapping, which is nothing but a case like in the previous slide I talked about taking a out sample or out time data to validate, right? So you just have to take multiple samples for that. Okay, so that is known as bootstrapping. So you just simulate future scenario, you simulate data from your historical data, and you just find out hundreds or thousands of such samples and test your model in these thousands or hundreds of samples and see whether the model performance statistics is consistent across all these samples. If that is the case, then the model is good, otherwise not. So you have to be very careful when you're using non-linear model or tree-based models like decision tree, or a random forest, and so on. If you're using linear regression, you need not have to do bootstrapping and so on. You just need to do the in time and out time validation. That will do. You can also use what is known as a regularization. Okay, so this is one such technique which takes care of model overfitting. This is particularly used where you do not have a large sample and you have just too many features which are very important in prediction. So in that cases where we're trying to capture the nonlinear relationship, we use some sort of a relationship regression and popularly known as lasso and razor regressions. We're not going to go into the depth of these regressions, but these are very helpful in cases where we have small sample and you do not have a large sample in place, but you have large number of variables in place, which can be very helpful. So what it does is that it actually reduces the coefficient values of so many unimportant variables, and that's how you actually reduce having large number of the effect of large number of such variables, and thereby reducing the uh, overfitting or avoiding the overfitting issue. So one important thing that I would like to say before we conclude is that when you're using or when you're building a model, and when you have come across such a case that you have built a model and then you found out that your model is overfit. So how do we go back and change the model, because you have spent a lot of time in doing that? So what could be the workaround? So one of the workaround could be increase the sample, but that's not the luxury all the time. You may not have a good sample all the time. So increase your sample could be one good way. Variable transformation could be another way. Transformation. So you could actually take the logarithm of variables, exponent of variables, squaring the variables, or maybe taking an interaction. So these are ways in which you can actually avoid overfitting in certain cases. And sometimes when you have already taken the transformations, you might have to get rid of some of these transformed variables. So you just have to play in, keep changing, and um, so either if there is no transformed variables, just include them. If there are already transformed variables, just remove them. That's the way to go about it. Other ways could be, if you have large number of variables, let's say for instance you have 20 variables in your model, just reduce some of the unimportant variables, keep it 15 and see how the model is performing. If it is consistent across your across in-sample and out-sample, then you have done your job good. So that's the way you actually get rid of this problem. Please subscribe to us for more such videos, and you can also visit our website. You can also contact us. Thank you.